All right. So we're going to go over molar conversions. This will be about simple molar conversions. But before that, we're going to introduce or reintroduce dimensional analysis. And dimensional analysis is the way we go about solving our molar conversions. And so dimensional analysis requires a couple things. The first thing is it requires a conversion factor. So here's a simple question. It says how many minutes in 4.23 hours? So the conversion factor we're going to use is the fact that since we're going from hours to minutes, that 1 hour equals 60 minutes. So it's important to first figure out what your conversion factor is, and then you perform the dimensional analysis. And dimensional analysis is just the converting using conversion factors in fraction form. And so here I'm going to multiply by the conversion factor. I have to choose which to put in the numerator and denominator. So like what part of the conversion factor. And I'm going to choose to put the 1 hour on the bottom and then 60 minutes up top in the numerator because this allows me to cross cancel my units. So the way we determine what goes where is based off of the ability to cross cancel units. And so if we do that, our final answer is going to be in minutes, right? Because that's the only unit that has not been canceled. And so you get 253.8 minutes. Then since we did math, we have to check sig figs. So 4.23 has 3 sig figs. 60 minutes in 1 hour actually has an infinite number of sig figs. And the reason is because 60 minutes is exactly 1 hour. It's not like it was rounded or anything. It's 60 minutes is actually 60.000 minutes. It's exactly it, right? To infinity. So it has an infinite number of sig figs. It's what we call an exact conversion factor, an exact number. And so we're going to round to the lowest number of sig figs, which is 3. 3 is lower than infinity. And so we're going to keep these 3. So our answer will eventually be 254 minutes. Okay. Just another example here. So how many minutes in 6.543 seconds? So our conversion factor, we're going from minutes to seconds or seconds to minutes. And it doesn't matter in which order you put the conversion factor. So just 60 seconds in 1 minute. And so then we'll have 6.543 seconds times, and then I'm going to put seconds on the bottom because that allows me to cross cancel 1 minute on top. So in this case, you'll see we're dividing. So if we take 6.543 over 60, that equals 109.05 minutes. This has 4 sig figs. 60 seconds in 1 minute isn't exact, so 4 sig figs is what we're going to round to. So it's 109.1 minutes. There's your final answer. So what are some conversion factors we're going to use in this unit? And here are the 4 conversion factors. So you have mole. If you want to convert to mass, you can go mole to molar mass. If you want to convert to the number of particles, you use Avogadro's number. The volume of 1 mole of the gas is 22.4 liters. STP is the standard temperature and pressure. So standard temperature is 0 degrees Celsius, so freezing. And standard pressure is what we feel on Earth. We call it 1 atmosphere is the unit we use to measure it. And then density, you can actually convert between mass and volume, grams per milliliter. This is a really helpful roadmap because it gives you it gives you how to get to certain places or convert to certain places, and we'll use this roadmap. It's good to get down, but we'll use this roadmap in the next problems, and so it might be more helpful at that point. So the first problem says to determine the number of moles in 8.0 grams of oxygen. So we first have to figure out the conversion factor before we do dimensional analysis. And what we want to do is we want to determine the number of moles, and what we're given is the mass, right? So we're given 8.08 grams. We want to figure out the moles. So we're given the mass, which is right here, right? And we want to go to mole. So to get there, or to convert, we have to use molar mass. All right, so let's figure out the molar mass. So we first got to figure out the conversion factor. So the conversion factor is kind of like a bridge to get you there. So the conversion factor, let's just put CF for conversion factor, just to make it a little faster. So conversion factor is, so we know 1 mole equals, and then, so let's do 1 mole of O2, oxygen, remember it's diatomic, is, and then the molar mass, so there's 2 oxygens, each oxygen is 16.00 grams, so it's 32.00 grams of O2. That's our conversion factor. Then what we do is we start our dimensional analysis. Here's our 8.0 grams of oxygen, and you can see there's 32.00 grams of O2 for every 1 mole of oxygen. Now, this allows me to cross-cancel the grams of oxygen. So 8 divided by 32 is going to be 0.25. If you notice, there's 2 sig figs, and here there's 4. 1 is an exact number, and so 0.25 moles of O2. My lowest number of sig figs is 2, and this answer is 2. Okay. So that's my answer. The next one is this: how many formula units in 0.5 moles of calcium chloride? So we're given moles, and we want to get to formula units. So formula units are particles, right? Remember, there's 4 different types of particles: ions, atoms, molecules, and formula units. Formula units are for the ionic compounds. All right, so let's take a look at our, oops, wrong one. So let's take a look at our molar conversion. So we are given moles, so we are here, and we want to get to the number of particles, right, which is here. So what do we got to use? We got to use Avogadro's number. All right, cool. So let's do that. So our conversion factor is going to be Avogadro's number. So our conversion factor is 1 mole of calcium chloride equals, and then Avogadro's number, 6.022 times 10 to the 23rd. Formula units, right, or particles, formula units of calcium chloride. All right, so we start with 0.5 moles. Also notice, and I do this, I think this is actually important, and it's not, in this unit, it won't be as important, but as you move on, it's important to actually include the name of the moles. And I know it's extra writing, and I know that maybe some of you don't want to do it, but I have found, and I don't like to do extra stuff, but I have found that putting the formula name, because as we move forward, we're going to actually calculate where we have different formulas or chemicals we go between, and so it's important to keep track of it all. It's kind of like bookkeeping. It's not fun, but it's necessary. So I'm going to take a look. I'm going to take a look at my. Here are my 2 conversion factors. So on the bottom goes 1 mole of calcium chloride. On the top, 6.022 times 10 to the 23rd. Formula units of CaCl2. That allows me to cancel out my moles, right, of calcium chloride. And so it's really half of, now this has 1 sig fig and this has 4. So we're only going to need to go to 1. So half of 6 is 3. So I know it's going to be 3 times 10 to the 23rd formula units of calcium chloride. All right, let's look at number 3. So hopefully you're kind of getting the rhythm of like, okay, where am I starting, and then where do I have to get to? So I'm starting with moles, and I have to get to mass. So what will get me between moles and mass? What conversion factor? Well, it's kind of in the name, but molar mass, right? So we're at moles, and now we're going to go back to mass. So we have to use molar mass, right? All right, so what's the molar mass of NaCl, right? Na is 22.99, right? And then 1 chlorine, 35.45. So the molar mass, or 1 mole of NaCl, its mass, is going to be equal to 58.44 grams of NaCl. So then we're going to start with 3.0 moles of NaCl And then we're going to use this, right, where 1 mole is on the bottom and NaCl, and then the mass is 58.44 grams of NaCl is up top. So this allows us to cross cancel, so 3 times that. Notice I need 2 sig figs, so I'm going to round this. It's like 175.32 grams of NaCl, but then I only need 2 sig figs, so that will round to 180 grams of NaCl. All right. The last one, we're going from, we're given 2.0 liters, so liter is a volume, and we're trying to go to moles. So we're starting with volume, so where's volume? Oh. And we're trying to go to moles. Now, we could go this way, but we don't have density, so this is a shorter path. It only takes 1 step, and here's the conversion factor, 22.4 liters per mole. All right, so our conversion factor is already given to us, 22.4 liters of O2 is equal to 1 mole of O2. So if you take 1 mole of oxygen and it would take up 22.4 liters of oxygen. It looks like I'm running out of space here, so I'm going to kind of move up here. So I start with 2.0 liters, that has 2 sig figs. 22.4 liters of oxygen is going to go on the bottom. Allows me to cross cancel 1 mole up top. So 2 divided by 22.4. So 0. And notice I'm going to 2 sig figs, so 0.089 moles of O2. All right. So hopefully that helps. There's homework I have assigned. This is just, you just need to practice. The more you practice, the better off you tend to be. Okay?